IMSc and he's going to tell us about black hole interior reconstruction radiation. What you will
Okay, thank you. Thanks for this invitation. I will be talking about black hole interior reconstruction from radiation. So this is based on some projects that I did with my students Krishna and Manish. So this is the plan. So I'll briefly describe the island paradigm or the island formula for a radius to channel black hole, which is in thermal equilibrium with the path. And then we'll discuss the reconstruction of black hole interior from radiation after the spacetime using a slightly modified version of the interior reconstruction proposal of Leutheusser and. So this is the setup. So we have an radius to internal black hole solution in J gravity, having inverse temperature beta, and we couple the two sides of the internal black hole to a bath, a non-gravitating bath having same temperature, so that there will be an equilibrium between the bath and the black hole. And this combined system can be conveniently described as a region in a plane. And the coordinate that we use for the plane is the crystal coordinates of the black hole. And this geometry, like if you look from the perspective of black hole, it's not classically different from an radius to internal black hole with reflecting boundary conditions. But quantum mechanically, these two systems are very different due to the fact that there is a constant exchange of matter between the black hole and the bath. So the moment a Hawking radiation escapes to the bath, immediately a quanta from the bath will be put back to the black hole system.
So you're putting reflecting boundary.
No. Here it's actually here you have the black hole, and here you have the bath. So there is a transparent boundary condition, and the system are in thermal equilibrium. So to keep the equilibrium or keep the.
So it's just a bath like in the usual setup.
Yeah.
So then why is it immediately, I mean, the black hole will just radiate out into the bath, right?
Yeah. So the moment one energy goes to the quanta goes to the other side, to the bath side, to maintain the equilibrium, another a quanta from the bath will be.
Oh,
getting into
you're
the-
setting it at eternal.
Eternal.
So you have light shining in from infinity at exactly the same rate at which it's
Exactly.
evaporating.
Yeah, that's true.
Got it. All right.
So that you maintain the eternal black hole.
Sorry, very naive question. What's the significance of that asymptotic infinity? That seems to be the infinity of Minkowski.
Yeah.
So why is it like that? Is that like the standard? The path is the path asymptotically Minkowski?
Yes. It's actually a flat.
Okay, you didn't say that.
Yeah. So it's a non-gravitating bath.
Yeah, it's
Such
not
that-
gravitating, but wouldn't it be
Just to make sure that there's a
asymptotically
continuity in the metric, there will be a Weyl factor. But up to that, it's a flat metric.
It's a non-gravitating bar, but it has gravity, right? Because it's equilibrium.
No, it's actually you don't have gravitons in two dimensions, right?
Right.
Yeah. These are like the matter.
You have massless scalars.
Yeah, some CFT.
Does this construction make sense in higher D? I mean, even if one can't solve it,
Uh,
the same construction.
I haven't thought about that.
Yeah, well, I mean, to the extent that you can have D brains, which are near extremal, which are asymptotically, say, higher dimensional flat space. So like D3 brains, are asymptotically flat, but then you can try to make them charged and make them near extremal. Then you get something similar.
And in that case, there are gravitons.
In that case, you have
In
gravitons.
that case, it's question of price.
So what was your question?
The bath has gravitons, but there's no direct gravity. So in such that there's massless free particles floating.
Yeah, there's some scalar field.
Here you have scalar fields, which are like a proxy for gravitons.
That's electronic.
There's some another CFT that you.
So the black hole can't emit gravitons because
Here,
yeah.
here there are no gravitons.
No, in higher.
No, it would emit.
Then there's a graviton in the.
Oh, yeah, so in the setup, I'm saying you have all of whatever type 2B supernovae.
So in that case, the bath is not strictly non-gravitational.
Oh, I see.
Okay, I'm sorry, I don't fully understand. What was the question?
No, I thought.
Can you ever have a was this the question? Can you ever have a non-gravitating?
Yeah, that's what
Oh,
we say.
yes.
But here, so it's a thing of two dimensions.
Yeah. Right. Yeah, so if you consider
Okay,
the higher
sorry, I
dimension,
haven't understood. Could you actually have a non in higher D and
Higher rear it seems like.
yeah, so the gravitons will escape to the path and definitely then there will be presence of gravity, right? So quantum mechanically, these two systems are different due to this exchange of matter between black hole and bath. And what it does is it actually builds an entanglement between the bath and the black hole. Okay. So if you assume that the matter in the spacetime is a CFT having some central charge C, at some late boundary time, one can compute the entropy using the usual replica trick and see that at late time, the entropy of the black hole or equivalently entropy of the bath will linearly increase with respect to the time. So this is a system that was considered by Baldacina, Lecoux, and Almeri. So they actually think of this as a model of black hole information paradox. So here what happens is that at sufficiently large time, the entropy become bigger than the thermal entropy of the black hole, which is not allowed. That's why it's a paradox. So you need to resolve this paradox. So what they do is they say that, see, this system that you have constructed, you think of as a full JT gravity system and consider the full quantum mechanical definition within the full JT gravity. And you write up, you compute the replica, or when you compute the entropy using replica, you make sure that you do path integral in the JT gravity, and when you take the Gn goes to zero limit, let's say the semi-classical limit, you do it in the correct way. That means you should be taking the right saddle as the approximation. So before spacetime, one can see that the right saddle is the usual this geometry, and once you cross the spacetime, then the saddle should be not just placing this W planes. Instead, you should connect the gravitational regions of each copies in the replica through a wormhole. So this is the
This is a Euclidean calculation.
yeah, that's a Euclidean.
The original problem was a Lorentzian.
Yeah, so what one does is the state you construct from the path integral, and then you do the computation, and then you take the Lorentzian continuation. And assuming that all this will go through.
I mean, suppose you should go on, but I mean, I don't find the proposed resolution so satisfactory because suppose I'm a Lorentzian observer, I'm quantizing gravity in Lorentzian space, right? Why should I suddenly adopt the iron? I quantize, I take these slices, I go through the black hole interior, I quantize gravity. How do I see suddenly that the region inside is duplicated on the side? I mean, it's a Lorentzian problem to begin with.
But is it don't create a Euclidean path integral or other way to do?
You could do canonical quantization like we do with states and so on.
Okay, so in principle, there could be a different resolution in canonical one.
Yeah, but this is
This is assuming we go through the Euclidean.
Yeah.
Yeah, but to state the problem of information loss in Euclidean path integral, then you have to work with S matrices or something.
Yeah, but I don't think that's stating the problem of information. I think that's what path integral is done in Euclidean.
But to answer what question? See,
To answer a Lorentzian question, that's all.
yeah, but it's different from like we can do an S matrix calculation by doing a path integral in continuity, right? That's not what's done here.
Here, I mean, they're just looking at the entropy.
They're just looking at the entropy and saying there's another saddle. Right?
But does the entropy, by virtue of the replica,
So then the question is like whether this replica trick itself is the right thing to implement.
Yeah, I mean, the question is, the replica, okay, so there are two calculations to do. One is you could say, I'm going to be interested in the entropy in the radiation outside.
Yes.
But because the radiation was created by the black hole and so on, I'm going to use semi-classical techniques and allow for this other saddle. And that gives me the correct entropy of the radiation, right? Okay, but I mean, is that a prescription or is that a proof?
It's not. I mean, yeah. If you use the replica trick to compute, one say that this is the right thing to do. But if you say like you have an independent definition of entropy instead of using replica trick, let's say by referring to the canonical quantum gravity in the Lorentzian signature, let's say by using something like operator algebra, where if somebody comes with a definition of operator algebra and full quantum theory, and then use a definition of entropy defined in that setup, then one can see how to define entropy in full quantum gravity and then take the semi-classical limit. That then I would like to take to that side, but I don't know whether, but anyway, I have to depend on the Euclidean construction. Since I don't know how to do that in the full.
Yeah, what would be the meaning of the fact that you're using different saddles in the canonical configuration?
That's what I don't know. Like, what are the states? What is the map to the? I don't know what is the full Hilbert space of quantum gravity and how to map each thing.
It would have to mean that there's a drastic breakdown, and even though these slices lie in a very smooth semi-classical region, there's a drastic breakdown of them. It would have to mean that.
For the purposes of computing very microscopic. You calculate more fine, so straight.
But it's not a very fine-grained question in canonical gravity because the Britannica is sitting inside on this slice and the radiation is sitting somewhere else. And you're saying this description is totally invalid. Even though the slice is in a completely smooth geometry. This is I'm just restating.
Yeah.
So as stated, it's not a very fine-grained question.
Yes, no question.
Yeah.
How much is the path relevant to this
Okay.
question?
I mean, I'm just saying, you know all this.
The question would still be there without the path. Or is it because since, I mean, I haven't understood it. Maybe you need this change of canonical configuration to accommodate the fact that there is a path. Makes it a different.
I mean, the question requires the black.
Canonical configuration.
The question requires the black hole to evaporate. Not.
That it would go without a path.
Yeah.
Yeah, so the
Basically,
path is just a surrogate for what the black hole.
Yeah. But to me, it looks like one has to understand the Hilbert space of quantum gravity and then define what you mean by splitting. I mean, looking at the subsector and then how will you compute the entropy? All those require a lot of work, I think. Without that, I don't see like some random intuition can solve anything. So what practically we have is the Euclidean construction. So better
So let me
ask
ask
what
a
happens
more
there.
practical question. So how is it that this Euclidean prescription, maybe this is well known, but translates into this particular knowledge?
Yeah, that I can. Yeah, maybe you can explain. So the replica trick requires considering n copies of this geometry and then connect all the cuts appropriately and then let gravity to do whatever it is allowed to do with the prescribed boundary condition. So one such possibility is that don't connect the gravitational region, keep them disconnected. So that is the trivial saddle or the Hawking saddle, and you can allow the gravitational region to connect each other. Since you are looking at the semi-classical limit, make sure that this geometry is a solution to Einstein's equation with no conical singularities or any sort of smoothness issues. Okay. Once you have that, you take this to be the leading contribution, provided you compute the free energy of this geometry and compare with the trivial saddle and make sure that this free energy is less than the free energy of the trivial saddle. Okay. And once you have this geometry, what you can do is, how will you get this picture, right? So what you can do is you can actually get the interior, the connected wormhole part by saying that this geometry can be obtained as a sheeted geometry construction. So you take W planes and figure out how can you get this geometry, precisely this geometry up to some conformal equivalence by considering n copies of W planes with appropriate more modified cuts. Okay. Now, if I introduce cut in the inside region, basically if I look at the so if I look at the W plane, so in the Euclidean picture, it will be like so this will be like a plane, and inside there is a disk, and the disk with green region, that is the gravitational region. So if you introduce a cut in the gravitational region, then you repeat the fluing procedure that will give you this.
So this island is supposed to be the kind of cut that we do in quantum field theory to compute entanglement.
Yeah.
A similar kind of
Yeah,
cut.
so the cut will be extended.
So in the n copy case, it will have some angular this thing around the island endpoint, and then in the end,
So there will be a
it
conical
would
deficit
be,
there. Yeah.
It would be like the artist.
Exactly.
So this island is like the artist.
Yeah, it is like that. So like Abhijit was saying, the moment you change the saddle, then in the Lorentzian picture, when you do the entropy computation, that's like introducing or associating a region to the path that includes the black hole interior. Okay, so it's just reinterpreting the wormhole solution or wormhole saddle in the Lorentzian picture. So that give you the when you take n goes to 1 limit and then do appropriate entropy calculation, that is equivalent to computing the entropy for these 3 Brouillets.
And now, given the fact that there is this weird thing, what does it mean for the, let's say, for this canonical quantification?
I mean, now the point is that the way
So I should understand the spectrum as the spectrum living in n copies in the n going to 1 limit.
Yeah. So now the point is that if somebody gives you this picture as a resolution for entropy paradox, it looks like a cheating in the sense that you are creating the Hawking phase at this horizon, and one part is going to Scribe plus, and one part is going to the interior of the black hole. Now, the moment you include the island, that's like saying that the pair that went inside to the island now has access from the Scribe plus. So you are because these 2 regions belongs to the bath now.
Yeah.
So bath has both the part of Hawking pair.
Sorry, how I thought island was just a cut along which I'm doing things. Right? And then
That's true, but the point is that this cut, you have to look at the domain of dependence of the cut. Right? So then if you create a Hawking pair here, the reason for the increase in entropy is that one part of the Hawking pair goes to the Scribe plus, and another part goes to the interior of the black hole. So these Bell pairs are the one which actually increases the entropy. Now, the moment you introduce the island to the path, that means the part which went inside is already captured and given to the path. So that way,
because of these connections.
Because of this connection. So if there is no replica trick or there is no such saddle calculation, I find it very difficult to even approve. So it's like a cheap solution. But given that there is an argument, then maybe one can accept. Otherwise, it's very difficult to even accept it. It's like saying that, see, the pairs are already given to the bar. So naturally, the entropy will come down.
What do you think?
Nothing. I'm just saying this island is somehow purifying the.
Yeah, it's basically purifying the bath. Okay. So the replica wormhole introduces a non-trivial entanglement island for the bath, which contains the black hole interior.
But just to say, this is like a standard entanglement by reconstruction,
Yeah.
right? It's not like a new.
Right.
I mean, in entanglement by reconstruction, the story is that you pick some boundaries of region and you look at its extremes. Then everything is subtended between the domain of whatever. Domain of dependence. The region that in the end is from this quantum error correction point of view, it's encoded in them. So now this new quantum extreme surface makes this
middle
region
small one
to be part of the entanglement mesh. Of the bath. So if you believe that story, then you can encode everything.
So that's you're saying standard RT kind of
Standard entanglement reconstruction.
models in the equivalence. If I do the construction, if you compute the segment, I will just end up with that.
Yeah. Yeah, it's basically because the generalized gravitational entropy kind of definition that one uses.
So you could not reconstruct the region past the island from the boundary of variance. Right?
Yeah, exactly.
So therefore, it should be reconstructed
From the
That's
bath. Yeah, right.
And all this can be done at 0 cells.
All this can be done.
Meaning
Well,
intersection of lines.
it's slightly not too close here, right?
Oh, some page.
After some page.
Yes, yeah.
Yeah.
But just to say, I mean, suppose one believed that information was lost, you could say, fine, I'm going to reconstruct the region up till the island from the ADS boundary. Consistent with ADS entanglement with reconstruction. And the rest is lost.
Yeah. That's true. That's not yeah.
Yeah. Well, that is true if no information is lost, but I mean, the crucial debate is it lost or not, right? So I'm just saying, could have been, just from point of view of someone really pushing this.
Yeah.
Okay, but I mean, I get the argument, it's very compelling. I'm just trying to say, I don't find, okay.
Yeah,
No, but if you were not resting on that argument, you wouldn't even say that you would let some island or something, right?
Yeah, so
To which you can be concerned.
could it not be, okay, just to take a contrary.
Yeah.
Could it not be that we say, yeah, what we learned about RT surfaces in ADS is great and so on, and we apply it to ADS too, and finally we go up till the island point and everything is reconstructed on the boundary. And to the left of that, it's not in the boundary. Now, how does it follow from that in the Lorentzian picture? Just to ask you, that it must be in the radiation.
We know that there's a boundary door is universal, so it must be. That of course you may regard as cheating, but from the gravity, if you want a gravitational argument, that you just follow your nose with the entanglement well reconstructed. Since the island is in the entanglement well path, everything that's in the island region is what it is.
Yeah, but nothing tells us that the path is some not. I mean, the RT formula don't apply to the path per se.
Why not?
I mean, let me take the view that, okay, I'm willing to, anyway, you should.
Okay,
go.
yeah.
Actually, maybe I can make a comment about this point. Actually, there's something which confuses me as well. So what I do is like, let's say this approach is right, then see whether we can learn something out of it, so that we can pose it in the full canonical quantum gravity without referring to the replicatory control. Do we have at least an in-principle way of doing it? In case, if we succeed, maybe we can answer that. So something which I would like to learn. So like, so given this island formula, what should we learn out of it? Okay, what is the assertion made by this island formula? It says that before the spacetime, precisely what Sandeep was saying, before the spacetime, the operators in the interior of the black hole can be reconstructed using the operators in the left and right exterior of the black hole within the gravitational region. So that means before spacetime, I just need the operators in this left triangle and the right triangle to reconstruct operators inside the black hole in detail. And after spacetime, if I use the operators that is inside this exterior of the black hole within the gravitational region, basically in these two regions, I should not be able to reconstruct operators in the interior.
So just a technical question. So the fact that there is an island, usually RT surface is then on the boundary. The fact that this is just in the bulk, technically at the technical level, it's coming because of the fact that the geometry has a Zn fixed point that is purely in the bulk.
Exactly.
It does not connect up.
No, that's true. That's true.
Okay.
Yeah.
There are two fixed points, maybe here and here.
Yeah.
Right.
That's
So that.
That's true. It's basically from the Euclidean point of view, it's saying that you have two fixed points at at two locations which are close to the center of the disk. Now, once you analytically continue, that becomes 2 points outside the horizon.
Have people seen islands in 3D gravity also?
There was some work. I don't. Maybe even BTC, right?
Yeah. This, yeah, I think, but for instance, Pennington's original paper was completely different.
Yeah. So he considers Schwarzschild, right?
I mean, what I'm saying is that maybe the replica wormholes are hard to construct in general dimension, but the QES is not so much.
No, but I mean, this is a nice, if you believe Euclidean path and people, this is nice that it's coming out of Euclidean path and people, as opposed to some sort of a description.
But the description, if you follow the description, it tells you to find this not trivial QES. That has been done in Ireland.
Yeah.
The construction of the replica.
But coming from this Euclidean path,
I don't think that's completely. There's some stuff.
And if I'm trying to do it, one would need to include the radiation region. So in IRT, if I'm right.
Yes. Yeah. So you need a.
That's what.
Yeah. So then we need some setup like ADS3 coupled to.
Yeah.
Right.
To some 3D stuff.
Right. But anyway, like after spacetime, it also says that it's not that just the black hole degrees of freedom should not be able to reconstruct the interior of the black hole. It says that now if you look at the triangles outside, basically the left and right path, use the operators from left and right path, then you should be able to construct operators inside the black hole. This is what island formula says, right? What island paradigm or the island formula, what it resolved is that you can see that you can resolve the paradoxical growth of entropy. Now, does that really mean that you will be able to reconstruct the inside of the black hole only from the Bach degrees of freedom observation? This is something which has to be demonstrated, right? Otherwise, why should some entropy itself is not something which you measure in physical systems, right? Because it's not a gauge invariant object. So why should somebody can say that, okay, this entropy, why should I care? The point which I should care is whether I am able to reconstruct the information inside the black hole from a protocol or not. Can I come up with a physical operation that gives me the information inside the black hole? So
it's from the
it's-
principle. And
Yeah. So you have to demonstrate that.
like, you're not happy with the fence.
PetSmart, whichever. Like I just want to see. Use PetSmart. Explicitly take a simple CFT and tell me how you construct. Give me the formulas, how you construct it. So there's something which I would like to understand.
Just to understand, sorry, I really have been remiss in not studying the PETS map, although you've emphasized it, but is what you're interested in the following, that now I have some state of the conformal field theory and not radiation.
Yes, yeah.
And it's some very complicated state, but explicitly show how the interior in that state is reconstructed. This is what you're
Exactly. In at least, is there any principle way like this is what you are supposed to do? If you can compute all, you should get the operators.
Sorry, how do you phrase this when in the traditional setup without the bar?
Without the bar, we will tell you like without the bar, at least in this case, you don't have this paradox at all.
It will not be that.
It will not be, I mean, and it's a pure system. Black hole itself is a pure system. You don't have any entropy growth. It's going to be constant. Now, so what I would like to do is the following. So I would like to know whether the assertions of island formula are true or not for the internal black hole setup that we already discussed. Okay, so what one can do is one can take the two-sided HKL as one possibility, or use the Papadopoulos statue proposal based on this idea of mirror operators, or use the Leutheusser and Liu proposal based on the idea of half-sided translation, which comes from the theory of operator algebra, which I will describe briefly. So you choose one of these proposals or any new proposal, PETSMAP or whatever, and then show me that the assertions of island formula are correct, at least within this setup. Don't forget about canonical gravity. Let's believe Euclidean setup and use a Euclidean trick. Can you show me explicitly? So the thing that
Kumka's point is that this entanglement is reconstruction. It's a general paradigm, right?
Yeah.
And there it is well known how to reconstruct the bulk operators.
Yeah, so give me that. I mean, the way in which at least I couldn't understand directly what are the explicit things that I'm supposed to do. Maybe it's just that.
How is it supposed to work for the radiation? I mean, I can believe that if you had an ADS theory where the boundary is the boundary of ADS, then okay, you folks have some reconstruction and so on. But here it's in the radiation which is going off to infinity. Is there a
In just this general theory of quantum direction logically right now and explicit.
even for the radiation?
You use some CFT in which the radiation is living and construct operator there.
Yes. And that operator is, it's a very complicated operator.
But we should not assume island formula. Directly from the without directly from the PETSMAP.
Yeah.
Will that take care of the wormhole correction?
Yeah, at the same level of Euclidean.
Euclidean, yeah.
Yeah, one has to use Euclidean.
I mean, for instance, the West Coast, the West Coast paper. Of course, you will do it in a different way.
Yeah.
I'm saying that
Yeah.
it's being done.
Right. So let's see like whether they're different or not. So let me since I'm going to choose a Leutheusser proposal, so I need some basic information from the theory of algebra operators. So I'll briefly mention what it means. I'm not an expert. I don't know full mathematical details of operator algebra, so I'll just describe what we need. So the idea is the following. So if you want a mathematical definition, it's this, an algebra of operator is an algebra of continuous linear operators acting on a topological vector space with multiplication given by the composition of matrix. So this is the definition of operator algebra in maths literature. But let's say if you have a quantum theory, how to understand it? So in a quantum theory with a given Hilbert space H, we define operators as marked from Hilbert space to Hilbert space. You define an operator by its action on a state, right? And you call an operator T as bounded operator if you when you compute the expectation value using any state that belongs to H, that expectation value should be finite. Basically, the matrix elements of T, all matrix elements of T must be finite. Nothing should be divergent. And collection of all such bounded operators has the structure of an algebra. So you take all such bounded operators and call that as B H. Then these bounded operator has a property that when you add two operators, or when you multiply two operators, or when you multiply a complex number, they are still going to be bounded operators. So that they form an algebra. Okay, now the point is study the properties of this algebra instead of looking at the state. So this is the drastic difference compared to quantum mechanics. In quantum mechanics, we always start from Hilbert space and study the properties of Hilbert space. In theory of operator algebra, you do the reverse. You just look at the operator, study the property, and one advantage is that, like people say, in most general setup, you can have operator algebra, but you may not have definition of Hilbert space or substates. So this actually covers a lot more. So interestingly, this theory actually started by von Neumann a long time back when people started Hilbert space. So the point is, we'll just study the properties of this algebra of bounded operators.
So just to see, I mean, if you just take a usual quantum field theory, the Hamiltonian would not be a bounded operator.
Yeah, it's a spectrum. Yeah, that's true. Yeah, that's true. Yeah.
And what would be an example in a quantum field theory of a bounded operator?
I will tell you some example. I will take simple examples.
You can just make some bounded function of that.
Yeah, so you need a smearing function so that there are infinities that can be cured.
I mean, I guess that's something like exponential IH. You have to IH.
Yeah, that's the IH. Yeah. Okay, so we'll briefly mention what you mean by a star algebra and then some of the associated concepts in operator algebra. So star subalgebra, you think of that as a subset of these bounded operators having the following properties. If you take any element in this subalgebra, they should be closed under scalar multiplication. You take any two operators in the subalgebra, multiply them or add them, you should get back an operator which is again the subalgebra. On top of it, when you consider the adjoint of the operators that belongs to subalgebra, the adjoint also must be there in the subalgebra. That is additional condition. Given if you have such a subalgebra, that subalgebra is called star. And star refers to this dagger operation. Okay, so all the adjoints and the operators are there within this subalgebra. Now you take such a subalgebra within the full bounded algebra bounded operators. Now look for all the operators that is going to commute with the operators in the subalgebra that you consider. Let's say you have a subalgebra M. Take any element in the subalgebra and look for operators that will commute with it. So there's a collection of operators that commutes with the entire operators in subalgebra M. So they are called the commutant. So if you have an M within BH, there will be a subalgebra that will completely commute with the subalgebra M. So this is the commutant. Okay. Now, such a subalgebra is called von Neumann algebra if you can show that the commutant of the commutant is the original algebra. Okay. If these conditions are satisfied, then you say that is the von Neumann algebra. So the algebra of our interest are always the von Neumann algebra. Now, let me give a simple example of this algebra of operators. So you consider this free scalar field theory in this plane. It has two decoupled pieces. The one that is moving along the plus light ray and the one that is moving along the W plus light ray. So these are, you can think of having theories defined on the light rays. And you consider two such things, like the one that is moving along the Yeah, so you draw lines like this, line rays. These two. So you define theories on this light rays, which are like the chiral parts. So you just take such two copies of free CFT where each copy has one chirality, the plus chirality or the minus chirality. And in that theory, you can define the current algebra. So you take the currents, plus currents and minus currents to be this, and then define the operator by taking this plus current and minus current, integrate them over a certain region with a weight factor, with a distribution. This will form an algebra. So it's basically O minus and O plus will form an algebra if you consider a diamond in the W plane, a causal diamond.
And I have like arbitrary in quantum field theory, very highly excited states where phi and so on have huge momentum.
Yeah, you can have.
Why would this be bounded? I mean,
No,
can't I have some
you
gamma?
should take your gamma. You should take your arbitrary.
Gamma dies out at last.
Exactly. You put a condition on the gamma. This distribution makes sure that whatever you consider are bounded operators. So you should choose the distribution.
It's localized in space, but also cuts off in momentum.
Exactly, yeah. Okay, so this O plus and O minus, if you consider a causal diamond delta A, where A minus is the interval along the plus minus direction, and A plus is the interval along the minus direction. You just take the product, basically you construct a diamond, and within the diamond, you construct these operators. So this is an example of
In the previous picture, where is this happening? Can you just?
here. So let's say if you're constructing an operator algebra within the bar, you could just consider a diamond here. We'll show you such figures.
But this W plane, by that you mean what? Sorry, I missed it.
It's basically this plane where we have constructed the glued geometry.
Okay.
Okay, so this is an example of operator algebra. Now, once you have a subalgebra, you can define this notion of modular flow. One can think of this as the symmetry transformation of the subalgebra. What it does is we take all transformations that actually keeps the subalgebra M and its commutant invariant. You just keep them within it. It's basically what it does is more like reshuffling the operator algebra. Okay. Now, such a transformation can be constructed out of modular Hamiltonian. Okay. If you have the modular Hamiltonian for the algebra to be Km and the commutant modular Hamiltonian is Km prime, then the full modular Hamiltonian for M and M prime, that will be Km minus Km prime. Okay, this operator will generate the modular flow. So in general, it is a non-local transformation. It may not have point action. By that, what I mean is if you take a operator which is localized in certain point, it may not be that it is just taking the operator to another point by following a trajectory. It may be a completely non-local transformation. We'll discuss both examples.
Just to make sure it keeps the subalgebra invariant, but just the elements
How
are.
we shuffle it, right? And it's a one-to-one mode, so that we don't. So let me give an example. So you consider this 1 plus 1 Minkowski space-time and define this chiral theory that you have. And if you this green lines are the Rindler horizons, and you can take a wedge, this pink colored region or blue colored region. So you define the operator algebra there, and the operator algebra defined in this region I called M, and the commutant, due to something called Hague duality, it says that it actually are the collection of all operators that belongs to a region which is causally disconnected to the blue region. So the red region, if you define operator algebra, that will be the commutant of it. Okay. So now, once you are given such an example, you can ask what is the modular Hamiltonian for the algebra M and what is its action. So for this simple case, you can show that if you consider an operator here, that under the action of modular Hamiltonian, it actually boosts the operator to some other location within it. So for such simple cases, you have a local action for the modular Hamiltonian. So you can identify the modular Hamiltonian Km as the boost operator associated with the causal diamond. It's a boost operator that fixes the two ends of the causal diamond and also acts like a null translation along the boundary.
Can I ask a general question about these algebras? Supposing M has an operator that commutes with everything in it, then it will also be in M prime.
Yeah.
So
So these are the centers.
yeah.
Ideas.
So in that picture, then M and M prime, here M and M prime are disjoint.
Yeah.
So is it not possible to have an
You
overlap?
can have such algebras.
Will not be von Neumann or?
They are still non one Neumann, right? One
There
Neumann.
might be, I don't,
Yeah,
it's
yeah,
not
it is.
obvious
It
to
is.
me there will be.
I mean, there are. I mean, algebras which have the centers.
Okay.
We'll not be discussing
Okay.
that, but that concept is there.
But if there's a center, then this picture can't be right.
Yeah. For this case, yeah. So this case, you have a particular operator algebra structure. So this example will be a specific class of operator algebra, but this is not the most general one.
In one case, I know roughly speaking, you diagonalize the center, then for each eigenvalue of the center, you. And then you sum. So, so in that case, at least.
How does the model translations act on the bar operator?
I mean, here it's just the usual 1 plus 1 Leutheusser. I'm not talking about the black hole solution and the bar. When there we have to, I will describe such example.
I just meant like you're creating it from T, right, which only acts on actual theory and not the bar.
There's no bar.
No, there is no bar. It's just the usual 1
Oh,
plus
it
1.
is correct.
Yeah, the picture is taken.
Really sorry for the remedial question, since you explained so nicely. The fact that you do smear operators,
Yeah.
does that cause a problem in separating into M and M prime? Because, I mean,
You are performing the integration. Scaling is done within the region. Within the region. Within the region. So within the region, you should integrate and still make it bounded.
and then the commutant is everything smeared in
Yeah.
the opposite direction.
Yeah. You will see an example where such simple thing may not work. I will show the example of two causal lemma. There will be an additional complication. Okay. So now we will talk about this particular von Neumann algebra, type 3 one. I'm not going to go through the full mathematical detail. What we need is what do you mean by a type 3 one algebra? Okay. So the definition of type 3 one definition of type 3 one algebra is that if you have an algebra M and you can compute the spectrum of the modular operator, which is the exponential of modular Hamiltonian. And if the spectrum is covering the entire R plus 0 to infinity, then you call such an algebra type 3 one von Neumann algebra. So for our case, what we discussed here, the modular Hamiltonian is a boost operator. So it is guaranteed that the exponential of boost operator will have spectrum from 0 to infinity. So you will have a type 3 one algebra for this case. If you consider a causal diamond and the CFT inside, then the algebra will be type 3 one.
Sorry, you're saying the spectrum has to contain every point of 0 to
Yeah,
infinity,
yeah,
or
yeah.
just has to
0 to infinity. It's not discrete.
In particular, it's a continuous.
Yeah, it should be continuous. That's why, like, if you consider any subspaces in quantum mechanics, then you have finite. It's a finite matrix. The modular Hamiltonian. So it's not guaranteed. It's guaranteed that you will not be able to cover. So because of that, the sub algebra will be type 1. It won't be type 3. Okay, so therefore the algebra operators in a CFT defined inside a causal diamond is a type 3 one algebra. That's actually a good thing in the sense that it actually gives you one more structure. The type 3 one algebra has an additional feature. It comes with an inclusion known as the half-circle inclusion. So it's an operation on top of modular flow. Okay? It is really not a symmetry transformation of the operator. What it does is the following. The statement is the following. You are given an operation U of S, and this U of S, you act on the operator algebra. Then the operator algebra there is a parameter associated to this transformation. I will explain it more. But given that you have some operation U of S with the parameter coming, real parameter S, if you take that operator and act on the entire algebra for S less than 0, that will shrink the algebra. Okay. So that is an interesting thing. So if you, let's say for some value S equal to -1, the action is giving you another subalgebra N. If you know that fact, then one can write down an explicit form for UFS. What you have to do is you take the algebra M, compute its modular operator, take the subalgebra N you obtain from this operation, compute its modular Hamiltonian, then take this product. Delta M is a modular operator, take power it by minus IT, multiply with delta N with IT power. Then what you will obtain is a nice operator, e raised to minus ISG, where G is a positive operator, where the parameter S and T are related. So this is the guarantee that you have for type 3-1 algebra, provided you choose appropriate M and N. You cannot choose arbitrary M. For every M, there will be corresponding set of N's that are available. You cannot take any random subalgebra. It has to satisfy certain criteria. Once it is satisfied, then using these two subalgebra, you can form an additional operation called half-circle translation.
What is N prime?
Sorry?
N prime is the commutant of
N prime is a commutant of N, M prime is a commutant of M. So that actually comes from the definition of modular operator. Now, the point is that the generator of the half-circle translation can be given an explicit expression, which is basically take the model Hamiltonian of M minus model Hamiltonian of N plus the model Hamiltonian of commutant of N, then minus the model Hamiltonian of commutant of N.
So just to understand, so the statement is given N.
Yeah.
If there exists a suitable N, that is the statement.
Exactly.
Then the fact that you have then you can construct a
Half-circle translation operator. Right.
And what happens if you have an M and you don't have a suitable N?
I mean, in general cases, if the thing come with if.
Okay.
If you have this, then you have.
Okay. So there's some properties that N must have.
Yeah, N must have. Exactly.
That's
So any U of S that satisfies that may maps M to a proper subalgebra is not a half-sided translation? Or this is not a complete definition.
So
right?
the complete definition of this US also form a group, a continuous unitary group.
What should form? U should.
You should form. Basically that
But
each
earlier you said something like N should have some suitable
property that I haven't mentioned here, which is basically
But
saying that
that's also in the definition
within-
of half-sided.
yeah, it's within the definition of if all those things are satisfied. Basically, for example, you take subalgebra M, acts with the modular flow of the algebra M. Then for a certain parameter range, N should be shrunk. So there are certain conditions that has to be satisfied.
I see.
And what was the significance of taking S to be -1?
If I take S to be -1, this will shrink the operator algebra. If it is positive,
Any negative S.
yeah, any negative. If you take the positive value, then the interest.
Why? Saying is there any -1 as good as any other negative value, or it's a special value?
Minus, I mean, if you might, for this setup, -1 is a special value, given that you are associating a particular algebra. The definition of US comes with two algebras, M and subalgebra.
Sure.
So that will fix what are the parameter range S can.
Yeah, I'm just saying U diagram -2, M U -2 is not anything.
Then, and the point is that then the entire definition changes. That's it.
It's a normalization of S.
Yeah, it's more like that. Given that, but all the freedoms are there because I haven't specified what kind of criteria N has to satisfy. There things will change if you change the value from -1 to -2. I will give an example. Yeah, we are going to use this explicitly. Okay, so I will give an example like after this. Now the proposal of Leutheusser and Liu. What they do is that the following: you consider the modular flow generated by Km for an operator algebra N, which is in the causal diamond. Now the modular flow can be understood as the evolution of Cauchy slices that are restricted to the causal diamond. It's like the time of that causal diamond. Now, what Leutheusser and Liu says that once you have such a causal diamond, and if you are able to construct half-circle translation, then what half-circle translation does is it actually explains the evolution of Cauchy slice within the full space-time where the causal diamond is constructed. So it actually says that S is the global time, not the time that is restricted to the domain, to the causal diamond. So I will give an example and show you what they really do.
Right away, it's not clear with that.
I will give you an example. So basically, their proposal is that by living inside a causal diamond, you can give a definition of the time for the entire space-time where you have actually embedded this causal diameter.
Right off, it seems crazy to me. I'll tell
It's
you why.
crazy.
I take Minkowski's space and I look at the Rindler observer and you're telling me I can see what's going on the other side.
Because, I mean, I'll tell you why it's possible.
Yeah.
It's possible because of the notion of commutants. That if you, when you construct this or modular Hamiltonian, it's not only sensitive to the algebra itself, it also is sensitive to the commutant. It has some
It's like one
knowledge
of these Richter like things that I know what's going on in the moon, but I really can't influence.
No, but
It is not that.
Sorry,
It is not that. It is actually
Richter, commutant.
yeah,
Sorry, commutant is on this side.
Yeah.
So you can access that way.
right.
But I thought the point was that just use one side.
No, actually,
Just use one
I
side.
mean, that's why I want to emphasize this point. When people say one-sided, there are some catches, like the mirror operator of Subrata. When he says that there's a mirror operator, it refers to the global state, which means you have some information about the
Oh,
other
I
side
see.
also.
So even in this Leutheusern,
It has that information.
you have this other sided operator.
Exactly, you have.
Then it's perhaps not that subtle.
Second, please, sorry.
No, I mean, this operator, I don't know how this is gonna work, but the operator that he defined had this M part and M prime part also, and N part and N prime part also. And if you look at geometrically, it is on the other side. Right?
I will explain that.
Commutant of M was on the other side, commutant of N was also on the other
And
side.
Right.
you are including those guys.
Those has to be included. That's
I think
the,
it's less surprising.
it's less surprising.
Okay, sorry, I thought he was using,
Yeah, Richter talks about unphysical things also. This one is talking about physical things.
okay, then maybe I should wait till you explain.
That's it.
So it's not that surprising, it's so surprising.
It's not surprising.
It's just that it's hard to like. It gives you some way of reconstructing figures in the upper triangle.
But I mean, okay, I mean, then in a sense, okay, in Minkowski space also, if you're including the other side, you construct.
Exactly.
But I mean, okay, I thought
Because
you were
there's-
going towards a black hole where you don't have the operators inside, get them from.
Yeah,
Okay, anyway,
you
let's
just use one sided thing.
Yeah, so-
Let me wait.
Yeah, so whatever I'm doing is two-sided black hole. And the claim is that it can be extended to one-sided black hole. I don't know how they have done. It's again, like, to me, so far, it's clear till like Surat proposal. But beyond that, I don't know, like, but at least for the two-sided case, we should be able to analyze this and see whether we can understand the island.
Maybe you can give an
From-
example.
I will give you,
Because-
I will give you.
You guys are saying that if the fact that you know what the commutant is, has some information about the whole algorithm.
Yeah.
If the algebra is bigger than the commutant.
Because the operation is an operation where like half-circle translation has two properties. It can shrink the algebra for s less than 0. It can extend the algebra for s greater than 0. So what we will see is that Leutheusser uses the fact that for s greater than 0, it extends the algebra. And that extension, they are thinking of as Cauchy evolution within the full space. Okay, so that will give an example to make it clear. And the claim is that for black hole spacetime, this implies that operators inside the black hole horizon can be expressed as half-sided evolution of operators outside the horizon. That's a statement. This is the proposal.
Half-sided evolution means the same as half-sided
Translation, yeah. So let's consider a simple example of 1 plus 1 Minkowski spacetime and how it actually works. So again, the same algebra. So consider this blue region, give you the operator algebra N, and the right renderer wedge is the operator algebra M. Okay, you have two algebra. One is the right renderer wedge algebra M, and another one is the sub-region denoted by this blue region.
So in your figure, the M is that entire green region?
Green, yeah.
Green region?
Exactly. This is the right renderer wedge.
Yeah.
Okay, these are the two edges. Now, for this case, let me explain what are modular flows and what are half-circle translation. You take this blue region, and if you construct the modular flow for N, it's just the same thing that I described. It actually moves the operator. Okay. Now, for half-circle translation, what it does is it actually takes the operator and do the infolding. Infolding. Yeah, it actually follows a null trajectory to the inside of the renderer horizon. I will explain how it actually, how one can see that. So this is the thing, and if you have infolding, that is like taking a point in this Cauchy slice to another point in this full Cauchy slice.
So maybe the surprising thing is that if you were to just use those boosts,
Yeah.
or whatever this modular evolution, then you could just do that.
Yeah.
And that will not take you inside.
That will not
neither for n nor
No
for n.
problem. Yeah, but if you
Together-
combine them,
Together.
yeah, exactly. So this is the picture. So if I take the boost operator for n, it will boost it like this. And the boost operator for the other one, it will boost the other way. So the combined effect is a translation.
Yeah.
So it's a combination of two boost operations. Yeah, but it's like, it looks like it's local thing, but it's more than that. So
Okay, but let me ask the question here, so you
Ah,
can
sure.
answer it, right? Okay, you do your boost, whatever.
yeah.
But there's no way, if I just gave you the information in the green wedge and
No,
it's blue subtle, you know what's going on above, right?
no.
So this is a mathematical thing,
Yeah.
but it's not going to actually allow me to tell you
Exactly.
what's going on.
But what it can do is the following. So you take, so what is my definition of U? So one definition of U is that you take, if you're given two algebras, M and N, you take M, act with the observed translation, it will give you N. Now see which operation does that in the Minkowski case. Okay, you take this blue region. You want to blue region plus the red region. This is your full algebra, N and commutant N prime. You want to get that N and N prime from M and M prime by doing some transformation. So you take this right and left render wedge, translate it along y minus direction. It will give you N prime algebra.
So if you, so this was, I guess, the thing you were emphasizing, you have to include M and M, right?
M prime.
Otherwise you can't do it.
Otherwise, I can do it.
Then in a sense, you got everything, because you got the entire Cauchy slice there.
Yeah.
Probably.
Right.
Then at least, but is there something non?
Yeah, the non-trivial
What's
thing
the
is that-
non-trivial thing?
Yeah, the non-trivial thing is that if you maximum, how much region are you using? You are using this region and this region. These regions are not something which is trivial, right?
I guess this still a little bit not real in the sense that if you look at the density matrix of n, right, you are covering that blue region,
Yes.
right? So everything, if you know the density matrix of n, that's the blue region you know,
Yes.
right? If you know the density matrix of n prime, you know the pink region.
Yeah.
Completely,
Yes.
right?
Yeah.
And if you know the density matrix of m and m prime, similarly you will know the regions, but
Yes.
none of that has the black hole in it, right?
No, yeah.
But somehow still,
Yeah.
Black hole interior is contained because any operator at that high can also.
no, but that's together, if you have together, right?
These are also together.
They're also together, yeah.
All of A and A and they're all together.
Yeah. I mean, if you allow me Cauchy evolution, I mean, then everything is contained once you have that region. So what exactly is the?
No, but sorry, if you just act with no, I mean, if you act on both sides, then you can get it, as you're saying, right? But is this what this
Yeah.
construction is doing that?
Yeah.
So I will give you a non-trivial example where you don't have this intersection of some region to the black hole interior. In fact, the radiation case that we discussed has such property. Like to begin with, there is no intersection of n and n prime or m and m prime with the black hole region. Still, you can show that if you do the path integral construction, it actually will do some magic.
So what if S less than 0, how do you compare to?
S less than 0, S less than 0, it will be like taking one point here and putting it's pushing into the n region.
Sorry, so did you not say?
No, maybe. I mean, I'm just wondering, just to ask you whether I'm missing something that the Cauchy evolution is not part of some algebra, therefore it is not trivial. Is it something like that or no? I mean,
If you just look at the commutants of m and m prime or n and n prime, then the Cauchy slice information, complete Cauchy slice information is not there.
you look at,
You will have a restricted, the coordinate will be like for the right interval, the exterior coordinate, for the left interval, there is the exterior coordinate, right?
okay. One second, suppose I give you the green region, just let's start with
Yeah.
green region and its complement, M and M prime,
Yeah.
right? Now, if I had to tell you the above wedge
Yeah.
from that, I would need more than the modular Hamiltonian.
Yeah, you need
That
more
is
than
clear.
yeah.
But if I gave you Cauchy data on M union M prime, then I would know everything,
Yeah, that's
right?
that's true.
So in that sense, I would say, oh, now
Sandeep, this
it's-
is actually reinterpretation.
oh,
One thing is that no magic can happen. It has to follow from something, right? What
That's
you
what
are
I'm
saying
trying to
is that-
understand.
you
Is
see,
there
it is-
magic or-
right now, there is
Yeah.
no magic. There is no magic here or mirror construction. I don't see any magic anywhere. It's just that, like, exactly what you said. If you are given a initial data on this space, sigma 0 slide,
Yeah.
then you can evolve it and get what is inside,
Right.
right?
Unless you tell me that I'm not allowing an evolution operator that
Take you,
that goes up.
Yeah.
I mean, that's all I was trying to do.
Right.
Whether-
Yeah, that's
So for
what.
example, N is crucial for this construction, right?
Yeah,
But
N
that
is
Cauchy
crucial.
data thing suggests that only M and M prime is sufficient. But here, it's a little different, I think, you're just
Yeah.
only using this boost operators. And with the M and M prime, just cannot do that, right? Because you will just stay in those, like this. It's a bit non-trivial, but I don't know how
I
to
also, yeah,
put the right words to it.
something is being
We
said.
don't think.
Seems-
Yeah, I agree with what you said, but I see there are two-sided problems. All of these are, for instance, here the G operator is just the null constant, right? It's like smeared over all of data.
Well, basically what I'm trying to get at is that, let's say you have two parties, you want to do operations. There is one, you can do operations on this party or this party. That clearly does not cover all the operations which you have done together on the bigger unit, right? So if there is something like that, if I wanted to access the interior, it is clear that if you act with the unitary which acts on both the parties together, then you would do that.
Right.
But here it seems like you're doing separate here and a separate there, still here.
But it's not, yeah.
It's not really separate in the sense that I have to completely translate N and N prime.
Yeah.
That is possible only through the momentum for the full space time. Now, if I just want to shift N itself, then what you need is you just need a boost or a translation that is restricted to the right intervention. So that way you won't be able to get inside.
No, but finally, I'm just using, operator, this modular Hamiltonian of M,
N.
N and N prime and prime, right? So in that sense, those are kind of separate unitary operators.
Yeah.
Because I'm doing E to the M, E
Yeah.
to the this thing, right? G was E to the IS.
Yes.
So,
But you can't just do it arbitrarily, you do Km and minus Km prime. Kn minus Km.
so the fact that they don't commute is also.
But something I think
I will know you must go on, and I apologize for just along the spirit of, is there magic or not? Let me ask you just the following question. I mean, is the kind of sleight of hand the following, that, you introduce N, right? On the face of it, that's a subalgebra of N, what are you getting? But N prime is of course bigger than N prime,
Yeah.
right? And is that the point? Now you're going to allow both N prime and N, and now
Yeah,
I
so-
can take N to be very small, then is that the point?
No, the point is that maybe emphasized by Leutheusser and Liu, what we say is that U is an operation which satisfies certain criteria.
Okay.
Like, and if you assume that criteria are the only one needed, their claim is that without referring to N, they can reconstruct the operator inside. The whole issue start coming when you mention what is N, right? N has the problem that when you look at the commuted N prime, that has a region inside the render horizon, right? That is the which continues with, right? If I was just using information from the left and right render versions, then it's actually a magic that you're able to get something inside. What they emphasize is that for solving this problem, at least for generalized free field, you don't need to mention what is M. You just need to mention what is M, and you will satisfy certain criteria. 5 conditions they satisfy. You just solve for that 5 conditions. Then that will give you operator that is inside the render horizon. There, that is the thing they emphasize.
But maybe you're demystifying it by saying those criteria amount to including N prime. I mean, I'm wondering.
Huh.
In that
Exactly.
case, at least it begins to be interesting that you're someone, okay, please.
Those
go, please go.
axioms those set of 5 conditions can be solved for generalized free field.
No, but that will give you N, but how will it give you N prime? For N prime, you have to invoke that.
No,
that
you
is
don't
computed.
have to mention N and N prime. That's the point. That's what they are claiming. And that's what they have shown. For generalized free field, they are able to solve the 5 condition US has to satisfy without referring to N.
Okay,
I thought the black hole context is time band or
Yeah. I mean, those conditions, the moment you say that n also need to be known, then you lose the power. When they kind of try to emphasize that, see, without looking at n, I can solve the 5 conditions that US as an operation must satisfy. There are certain conditions US satisfies. They just solve for this condition for regular field.
They use some M and N. They use some.
They don't use n. Here, just to demonstrate how it actually works, they use
I
it.
don't think that there is any magic here.
Yeah, here there is no magic. The magic that there, what happens, even for this case, they can, what they claim is that they can solve this problem by just, here I am using explicit expression of U of S, right? I explicitly mention what is n, what is n.
Yeah.
And then I'm just telling you that what US is doing. What they do is, they just don't refer to n. They say that given an operator algebra M and assume that there is a half-circle translation existing, this half-circle translation will satisfy certain criteria, which can be stated without referring to it.
No, but just with the half-circle translations, what can I do? I mean, I'll just make it more, smaller and smaller and smaller. I want to make it bigger and bigger.
You take the parameter value S going to S positive instead of S negative.
I thought, I mean, if you have an inclusion, it's a many to one.
Inclusion, yes, inclusion, that's the additional thing that Honglu does. Instead of inclusion, you just look at the other direction. Look at S.
How can it possibly be? There's stuff, I can send a light ray from there. How can I?
Let me put it like this, that I have the same, I think, that, okay, you start with n, right? Now you have a subalgebra to begin with n, right? Now for some range, you are shrinking it. Say for some other range, you are expanding it, but you can't expand it past m, right?
Yeah. You can't expand it past m, that's the point.
So that means diagrammatically, if you start with the green region,
Yeah.
you're going to be stuck with the green region, right? So the power to look inside cannot.
It can be extended to inside.
How?
The m can be bigger. Mathematically, they don't say, but Honglu propose that, that's their proposal. If you look at S greater than 0, they solve the 5 condition and analytically continue from S negative to S positive. This analytical continuation is like the untrue continuation, and it will take you inside. That's the game.
No, but if you can send something from this side, right? On the left,
Yeah.
which will go and access that the top diamond.
Yeah.
And if you start extending, you will not clearly know that there is a some light coming from that region.
No, the point is that then once you extend from here, this region shrinks. So the commutant shrinks. If M increases, the commutant shrinks.
But okay, maybe I'm misunderstanding. You must go on, but maybe I'm misunderstanding. I thought the starting point was M, right?
Yeah.
Now in this picture, M is say the green right region.
Yeah.
Okay. Now N to begin with was at least a subalgebra. Then you have some operation.
Yeah.
Now that can extend, expand, or shrink or whatever, but it can't extend it past M, right?
It can extend if I continue it. That's the claim.
So there's some continuation.
From
What
S
is
left
this continuation?
S negative to S positive. That continuation there.
But that continuation has to be defined not within M, right? There has to be some M and N commutant. Okay, maybe you extend it in some way, keeping track of the commutant.
Yeah, the extension says that M enlarges, M prime shrinks.
So then maybe they keep, so implicitly in this picture, you are expanding the green right region instead of shrinking it.
Yeah.
By keeping part of the commutant in it somehow.
Exactly.
Then it's not surprising that you'll get access.
Yeah, so left side you shrink, right side you
But then it's not surprising that you'll get access.
Yeah, so it is, I mean, the formula that you get is exactly like.
I understand that. Yeah, go ahead.
So once you do the computation, what you are doing is, let's say you just want to construct an operator inside the black hole ingredient. The untrue continuation says that you need modes from right side and left side. This formula essentially gives that. It actually matches the
this
untrue
picture, you
continuation.
could have extended on this side, right?
Yeah.
You could have just extended, you could have put that red triangle on
Yeah, you
this
can
side.
do that.
And then that would be already part of your thing.
Yeah, yeah.
I mean,
So far,
for example, the bottom diamond already has some red part.
Exactly.
Yeah.
So you could have just, that way you are already making within a part.
What is the red part? Sorry, there is the pink and there
which is inside.
Yeah, this inside is already in that.
Goes inside.
which is the red?
The N prime.
Oh, this
that-
one.
Yeah,
Oh, that you're calling
yeah,
red.
it's already coming inside.
Yes, 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 yes.
So- So if you are using, I guess, this both M and N prime to do this half cycle
Yeah.
translation, you're already going into the black hole.
Yeah, yeah.
Now the point I'm trying to emphasize is that from their perspective, they kind of claim it as a magic because you don't, without referring to this N, they can solve the conditions, abstract condition US has to satisfy for generalized field. And they get a result for positive S which matches with Unruh computation. So the Unruh's continuation can be interpreted as half-cycle translation for S positive.
Yeah, but in physics terms, they must be doing something like this, right? Suppose I just had N. I have some density, please correct me. I have some modular operator, otherwise called the density matrix, whatever, right? And then I purify it in some way. And I declare that to be M prime. And then I say, okay, now I can grab part of M prime. I mean, something like this they've done, right? I mean, otherwise, in physics terms, how can you do some mumbo jumbo math? Just start with green region and suddenly start looking at stuff.
You need M prime.
You need M prime,
You need M
right?
prime.
So if
Yeah.
you say they have done it just from M, they have assumed some particular form of M, right? Standard pure.
I think there is something is that on CFT side, is a Microsoft Institute, you can construct, given M, you can also construct M prime.
Yeah.
Then once you have M and M prime, then you have the modular of it. But I mean, I suppose the practical thing that's hard to do is constructing M prime.
Yeah.
That, I mean,
Yeah, so in general, this thing is that, I mean, what they say is that I can give you an operator algebra description of infalling. That is the main point, but now I'm going to use it for practical purpose. Where all these issues are not there, I mean, we will have a clean, I'll show you that, I mean, I don't know whether it's satisfying for you.
And you must go on, I promise, just to understand what Onkar said. Onkar is saying in the context of ADS, CFT, if you knew the boundary region whose entanglement wedge is M.
Right.
Then in principle, in the CFT, you can construct the state of the system in the complement of that boundary region.
yeah.
Uniquely, huh?
Or, I mean, you could construct it in the CFT.
And you need that each other.
Yeah.
I'm saying, like
You
some,
need each other.
you have to make some assumption,
Yeah,
right?
yeah, you can add some unity on the other side and the multi-harmony. You can add some unity on the other side. That does not change the multi-harmony. Sorry, all the actions of multi-harmony and the smaller region. That's, so you need to take a statement. Yeah, we need to take a statement. So maybe with the choice of statement.
With some choice of
Yeah,
state, then you can,
You can figure out.
okay, yes, that is.
Some those if you were all confident.
So that's a mirror construction, right?
Can I ask just a finite dimension question, to get this straight? So if I have a state, a bipartite state, just finite dimensions, right?
This thing will not work.
P party A and party A prime, let's say same dimension.
Yeah.
And there's some state. Can I use unitary operators, any unitary operator on A? Right, I'm allowed to, let's say, do any unitary transformation on A and any unitary transformation on A prime, A bar, whatever. To create, can I explore the full
No, there in that finite dimensional, this thing itself is not working.
but isn't it roughly what is
Yeah,
happening?
special type.
It's only for type 3. It's not possible in quantum mechanics.
When you talk about the half-cycle fluctuation satisfying hypertension and all that, do you mean the half-cycle fluctuation or do you mean something that plays the role of PBM?
The U itself will satisfy some condition.
So that's not half-cycle fluctuation.
Yeah, the half-cycle translation itself, that operation US satisfies certain criteria. It actually satisfies certain 5 conditions. Provided you have this construction, such an operator will satisfy 5 conditions. And the case of claim is that this condition can be solved for generalized quickly without actually referring to it.
That's a technical mistake. Like I thought by half-cycle fluctuation you meant the one which leaves this algebra invariant, but not necessarily the commutative technique. Yeah.
Yeah, that's the U, right? Yeah, this one.
By you mean something that leaves both the algebra and its commutative.
Yeah, you will have both algebra and summation.
Then it's not a half-cycle. Right?
Half is not referring to that. Half is referring to the parameter range.
Okay.
For s less than 0, the t also should be having that t less than 0 notation. So that it's referring to the parameter range.
But I can think of you.
You can do it. Now, So the same thing can be repeated for the black hole, and one can compute that when you do the half circle translation, the point P here will be following a trajectory like this. So the interior construction is possible, whether there is some magic happening or that's a different thing. Let's say no magic is happening, this phenomena will happen. Basically, what this half circle translation does for you in a Lorentzian flat space quantum theory is that it actually give you a realization of space-time algebra and operator algebra. So the group of half circle translation will generate the Poincare algebra. So that was one big thing that happened in operator algebra business. You have a description of space-time symmetry within the operator algebra using an operator algebra operation. So that's some math.
But I mean, the fact that it is not quite working with finite dimension is already somewhat magic today.
Huh.
Right?
The point is that you need something like boost operator.
Thing which lets you access the full input space just by using factored unit.
Yeah. Yes, that is not.
That's the point, somehow they're not factored.
Yeah.
They are not factored.
They look like, I mean, in the finite dimension analogs of these things would be factored. But these are not factored.
So where exactly not factorizing? Because they are creating operators with M, right?
Yes. And I mean, the things that you're exponentiating are two-sided objects. They have no sense of scale.
I see. But then
Not write K as scalar plus or minus. That makes no sense.
I mean, for
because
practical purpose, you write down, but path integral itself take care of that. That the fact that they are not really factorized. Anyway, let's try to see, given the fact that you have some way of constructing or reinterpreting Unruh's computation using half circle translation, can I implement this for demonstrating the island assertions of island formula? Right? So let me see whether we can do that. So we would like to ask,
Can we show that slide of JT gravity again? So you're saying, okay, now same idea allows you to go to forward.
Yeah, that's true. Now, so we asked, can we use half circle translation or HST to demonstrate the assertions of island formula? So we will try to demonstrate the second assertion of the island formula, which says that before the spacetime, the operators in the interior cannot be reconstructed using only the operators in the path. And after the spacetime, they can be reconstructed using only the operators localized in the path. So see whether we can do that using half circle translation. So, like we will keep on saying, so let's try to choose operator algebra which is restricted to the path region. Okay, so you have an M, this full green region. There you have the operator algebra which is completely restricted in the right path, and you have a subalgebra blue region, which is again completely restricted in the path. So now we can ask whether can we use this half circle translation idea to demonstrate island parity. The immediate answer is that no, it cannot be used because of the fact that we will keep on discussing that the commutant will include the degrees of freedom from the black hole region also, right? So the commutant will include the ADS2 gravitational region. So it's not something after a translation, the operator US is constructed using both the degrees of freedom from black hole and the path. So from the beginning itself, you can't choose it. You can't use half circle translation to study island paradigm. Because island paradigm requires differentiating the path degrees of freedom and the black hole degrees of freedom. Right? You should come with an operator constructed only using path degrees of freedom and do the reconstruction. Otherwise, you are not doing island thing. Like you are outside the island paradigm. So half circle translation or the Leutheusser and Liu proposal as itself you cannot use for island paradigm. So what can we do? So what we can do is we can use the idea of relative commutant. This is a well-known concept in operator algebra theory. So what you do is,
sorry, in other words, I guess you could just take your M to be disconnected region, right? Is that what you're doing basically?
No, even if I take M disconnected, still there will be a commutant which includes the ADS2 region. Let's say you take operator algebra from here and here.
Yeah.
And the commutant will be this.
Which is what you wanted, right?
I don't want. Commutant should not be going to the ADS2 region. If it is going to ADS2 region, then there is no point in asking this question. Definitely it will reconstruct at every time. So it's outside the island paradigm. Okay. So what we do is we take.
Because you're using the commutant also.
Exactly. So
Okay.
already that has black hole interior operator. So what is the point of then asking anything?
But can I say one small thing? I mean, here we are taking the space-time notion of locality very seriously, right? Like you're saying something commutes. I mean, the whole point of the island formula is that what was inside and seemed to be space-like separated actually is not.
We will see that. At the end that we will get that conclusion from this analysis. We will get that.
Okay.
So the point is that we have to slightly modify the analysis by saying or introducing the notion of relative commutant. What it does is you can start with an operator algebra. And now what should be your commutant? You are finding commutant in the full space. Now instead of looking at the full space, you can look the commutant in a subspace. Right? So you define algebra associated with the bath itself. You start with a Cauchy slice defined at some time u, and then identify an operator algebra at that time u for left bath and right bath. Okay, you take this Cauchy slice and look at the domain of dependence of the path region. And in the right region, you have some dr, and left region some dr, and calligraphic dr and calligraphic dl will be the associated algebra. So now you ask for relative commutant within that bath algebra instead of asking into full space. Okay. So then you have the notion of relative commutant. You take your original commutant and find an intersection with path union of left and right path algebra. Okay, so that your relative commutant, instead of having this picture, will be of this way. So the relative commutant and the operator algebra both are in the bar space.
So the relative commutant of BL is BR and BR is BL, right?
Yeah, right, exactly. So this way we can at least get an operator algebra and its commutant within the bar. So now we can start asking. Let's generalize half-circle translation for this set. Okay. So we can introduce the notion of reduced half-circle translation, more like the reduced density matrix. So reduced half-circle translation, which only depends on the algebra of observables in the bar. Okay. This is a modification that we are actually doing. So RHST, the reduced half-circle translation, is defined as some UB with the generated GB, where the generated GB is Km minus Kn, and instead of Kn prime and Km prime, you use Kn prime B and Km prime B. M prime B and N prime B are the restrictions of commutant to the path algebra. Okay.
This is very funny because I thought when you define this outside the market and there was some calculation of dividend.
Yeah, that's true. So that's why, like, I don't know the full mathematical features and properties of it. Like half-circle translation, you know the full mathematical properties that it satisfies. I just propose this as an operator. It's likely to come.
At intuitive level, is it clear that this operator will have to show cancellation?
No, nothing at least. I don't know. I don't know.
Because of this you need this feature, right?
Yeah.
Which feature?
The one boost is this way, the other boost is this way with this intersection point being fixed.
Here there is no intersection point.
Yeah, there's far away.
They're far away.
And what I mean is what you put as your end.
So the M and N are the original one. So this one are the M and N, and the relative commutants are the one that is restricted to the left side. Okay, so the relative commutants for M prime and M and N will be both same at the left path algebra for this case.
Would it be that the GB is a better behaved operator?
I don't know. I haven't studied that detailed properties. This is something which, let's say, this is an operator. We can up to all. If what happens is that there could be some divergences, right? Yeah. So at the end, I'm not going to study the spectrum of this operator. I'm going to see how this operator is going to act on some other operator. And there will be a dagger and a U operation. So at the end, I hope that this divergences may cancel out. Okay. So I'm just inserting, I just want to take this operator, maybe a well-defined or not well-defined operator, and see how this operator is going to act on an element of operator algebra.
Can you show the N and N prime regions also?
Okay. So this one, like n prime, since this is like n is this algebra, right? Then its commutant will be. So this actually this is a lightweight. And the operator algebra is defined as the algebra within the causal diamond. And its commutant,
Shouldn't there be a little bit there?
no, this line is not included, right? Because if I declare that my algebra is within the causal diamond, then this lightweight will not
So
be
you're declaring that your algebra is with path.
within the path.
So you take commutant intersection with the path.
If
So there is a little piece there, a little triangular piece there, which you have not highlighted.
I mean it's not this one, right?
Yeah.
This line that will be lightweight.
No, I mean, if you go back, there wasn't there, that you just start, in other words, that n and n prime should touch each other at that point, right?
You mean?
Yeah, there's one small triangle. Yeah, just continue. Yeah.
Right.
No. The point is that the path algebra, PR is basically this. Yeah. This diamond, which matches with it. It's a causal. It's the domain of dependence of this slice. Path algebra.
But why
For
not
this
slice? I thought path algebra is all the operators.
No. I'm choosing a causal diamond because I have to have a type 3 1 algebra. And that is my choice. With respect to what I should choose a relative computer. I define the operator algebra for each time.
Okay.
Because at the end, in the entire process, there should be some time dependence coming, right? The time dependence is coming from the fact that the operator algebra is defined at each time. Otherwise, why should the behavior change after some time?
So, sorry, so just again, so I understood your region N. And then in your way of defining this, new way of defining the commutant with respect to this B object.
Yeah.
Then n prime is, are you saying equal to n prime? What is it?
Yeah, n prime is equal to n.
Let's see.
The
And
commutants are same.
that's because to obtain n prime, I would have to look at first the commutant of n in the whole algebra and then take the intersection not with this.
Yes.
And that only gives this region.
That only gives us.
The point with this operator does something nice. In the half-sided translation cases, it does something nice.
Nice, yeah, right. Sorry?
Here, what is the claim? Your new operator.
In this operator, I just take this operator and then define the half-sided translation and see what is half-sided translation or reduced half-sided translation is doing to an operator in it or in it.
Sorry, but if you did that for the ordinary Minkowski space
Yeah.
before all this, there, if you define your relative commutant, where you take those two M and M prime algebra and you declare that to be your algebra and you want to take relative commutant. So then you will take n here, which is small, but that n prime which extended, you will not have access to that string.
Yeah, that's true. You do not have access to that.
But then I thought things would break down already in Minkowski space because you don't have access to that string.
So that you won't be able to construct.
Yeah.
That's what I want before spacetime.
Oh, okay.
Before spacetime, I should not be able to reconstruct the operator inside the path or inside the black hole input. That is what is expected. So this reconstruction, this proposal at least matches the first assertion.
Can I just ask one more thing? I mean, just from the math point of view, some properties have to be met to define the half-sided translation. This, that, and the other, right? And are they tied to the fact that, if I had Rindler observers, I think this is what was being asked, but let me just make sure. If I had Rindler observers, the right and left modular operators are horrible, but the Minkowski Hamiltonian is nice, right? And so on.
They are not referring to any such statement. They are referring to the statement that if I act with modular flow, then the modular flow should be doing some specific things to the operators.
I should be, but maybe in the spectrum of the operator or something, does it go back in that?
Maybe what maximum can happen is that the spectrum of operator G, the one guarantee in usual half-sided translation is that it will be positive.
And here, do you know?
I haven't studied that.
Kind of question.
I haven't studied that.
The first question is that whether is it a good operator? In the sense that outside modular is not a good operator.
Half-sided?
Modular
Yeah.
outside is not a good operator.
Good operator in the sense that for me, it will just do the boosting, right? I just need what is its effect on another operator. I don't want to know what exactly that operator itself.
The question is about UV divergence at the point about the boosting.
At the point of?
About the point you're boosting.
Yeah.
About the origin.
Yeah.
So when you just do some outside.
Yeah.
That is not a good operation because there is some weak evidence on your origin.
But I can take any operator that is inside the diamond, somewhere here, and then do the boosting, right?
Boosting with infinity.
Yeah.
This boosting with something that doesn't make sense.
No, but the point is that the positions will be replaced, right? P will be replaced on P prime.
Why? Because that operator doesn't make sense. What are you going to boost with?
I mean, this.
I mean, if I take,
What are the rules of the game? Because
I mean-
you are
I mean, you
insisting
know-
that the operator should be finite and
you know what is the modular Hamiltonian for this region?
infinity.
Sorry?
Infinity.
It is a, I mean, infinity, I mean, when you refer to modular Hamiltonian, in physics literature, it just means one single interval. They don't talk about the commutant. They write down the boost operator expression, right? That can be done here also. In fact, that is what Cassini and all they are always doing.
So I guess the question is type 3 multiplied, and you could have retreated back to the type 1 setting and loaded this finding. And then everything factorized this and your operator makes sense.
But the setup that I have is all automatically. I'm not imposing anything on top, whether the algebra. This is my system and this is what I want to study. So what is that algebra? For me, I construct all the operators from the CFT language, right? So CFT tells me what is Kn.
Yeah, I'm saying, I guess, as Rohit was saying,
Yes.
that finite n, like, finite n, you could imagine working in a type 1 setting where
Yeah.
the black hole is coupled to some finite dimensional quantity.
Yeah.
And there, everything, all of these operators that you're writing down.
Okay.
I mean, the problem is if you try to write them down in the continuum, then they will make sense.
It may not recreate the island, you know.
Okay, I mean, at the
Yeah.
first stage, at least they're well.
Yeah.
Then we can discuss when we start.
Yeah, I was asking what his setup corresponds to, like, do the operators of left and right factor or what?
I have written down an explicit expression for. So when I write down this Kn, this is just referring to one operator algebra, M itself, one side. And this is expression what people keep on using. Okay? So it's the boost operator.
The thing is, if you're acting with this operator on another operator,
Yeah.
you're conjugating this.
You just take a contour integral
Yeah, right.
to find the action, right?
You say take an operator and
Yeah.
and conjugate that operator with e raised to pi k.
Yeah.
That is fine because what happens is, I mean, even if you have added like k and prime
Yeah.
in this expression, that would have cancelled.
Yeah.
But you will not use e raised to pi k to add this operator on a state.
I'm just going to use them. I just want a similarity transformation. I just want to act it from both sides. I don't want, I no way I will keep just looking at this operator only. I always want the conjugation. So this operator is used for doing the conjugation.
I mean, then you could have added like the operators in a formula in
Yeah.
your new key to title. And that wouldn't have like changed anything, right?
What is that?
So
This is
in
the,
this expression, in the expression that you had,
yes, yeah.
could you have added like k and b and minus k and b? Would that change anything?
I know, then the point is that KMB itself is something which includes the operators from the black hole region, right? From the gravitational region. I don't want that. Because if I include that, then the purpose of this question is gone.
Okay, maybe you can go ahead.
Now the point is that about this cancellation of infinity. I haven't seen any calculation in CFT language where they really require that. They just have an operator description and use the OPs computed.
As long
Or as long as all the epsilon, 1 by epsilon things when you compute the entropy, right? When you compute a number out of it. But I'm not going to.
balancing this,
Yeah.
this is not a well-defined operation on a state.
On a state.
This operator with say, like for conjugation.
Yeah, that's what I'm doing. I'm not going to use it for acting on a state. In fact, even the state itself is not known to me, right? Because it's type 3 1, there is no notion of state in that sector.
No, but you could have defined as like it was saying even for flat Minkowski.
Yeah.
Right.
Even for flat Minkowski space, if I look at all diamond, I mean, in the full mathematical section, there is no state you can associate to them. There is no Hilbert space there.
I mean, you're defining these modular operator for a state, right?
No, it's not for state. It's for operator algebra.
No, the operator algebra is constructed on top of that.
No, actually, there is no. If I look into a subalgebra, I don't have a notion of state. If you are talking in the mathematical language. So if you are okay with 1 by epsilon, then yeah, we'll, both of us can. Yeah.
Maybe we can go ahead.
Yeah. So then, like we were discussing, with this choice of algebra, naively, or if I don't worry about any other thing, it won't be able to reconstruct an operator which is inside the bar, inside the black hole, as expected. Now, what happens after phase time? So that require you to make some assumptions. That the notion of half-circle translation or reduced half-circle translation, whatever we are doing, was for a conformal field theory or a quantum field theory in a fixed background, right? For gravity, where you make the space dynamical, space-time dynamical, I don't know whether such definitions exist or not. Basically, the theory of operator algebra, I don't know whether it's developed for quantum gravity. Right? For, let's say, for JT gravity itself, do you have the notion of, within the full JT gravity, do you have a notion of algebra of operators and after a translation? I don't know. But let me assume that they exist, that it can be defined in the full path integral, full gravity. Then
There is this type 2 that people talk about, right?
Sorry?
And that also is outside.
No, they don't.
In the bulk, I mean, you have to start with some notional gravity or something within your entanglement, right? I mean, we need to be careful, right? We need to stick to
Yeah, so I mean, I don't know like whether such construction exists or not. What I'm going to assume is that, let's say this operator can be defined within the full gravity setup for a subregion.
Maybe you can take the point of view that there's some weird saddle and you're just doing semi-classical.
Yeah, right. Yeah, the point is that I have, let's say this operation that I have here can be defined in full JT gravity. I don't know whether such thing is possible or not, but it's useful to study that. Let's say you come up with a path integral description of this operator, and then see whether that description satisfies all the properties a half-circle translation should satisfy. Which I don't know. I haven't seen anybody constructed it. But I'm going to assume that, okay, let's say this thing can be extended to full JT gravity path integral. And then I ask whether such a description, whether the description that we have in the booking saddle, or the one that we are talking about, whether that is a saddle point approximation of the full JT path integral. Okay, so one assumption is that this operation exists in the full gravity and that has a path integral description. That's an assumption. And whatever I have, let's say I missed something. So I will come to that one. So I'm going to assume that the RHST, the reduced half-circle translation, can be studied within full path integral for full JT gravity. And just naively then assume that you find a path integral description of half-circle translation that we discussed by using the fact that half-circle translation operator can be written in terms of reduced density matrices. Just replace each reduced density matrix with this associated path integral description, and then see whether that path integral is a semi-classical limit of the full JT path integral. Then one has to ask whether the saddle that you have chosen has the right free energy, like we do in the case of replicator. Are we choosing a saddle having least free energy? Okay. And it may happen that the saddle with which you started, the thing where you have a fixed background, may have a time dependent free energy, and later it may happen that there is another saddle which has least free energy. And if you change the saddle, it may happen that the behavior of this half-circle translation may change, like in the case of entropy. Just assume that is going to happen. Now the point is to see what is the gravitational description or the saddle description of this half-circle translation that I already discussed, and find its computed center of free energy, see the behavior, and construct another saddle like a wormhole saddle, which may describe the half-circle translation and see whether they have least free energy or not. And once you figure out such a saddle, repeat the entire computation and find an operator description of the new saddle. And this is the idea that we would like to pursue. Okay. So to begin with, so what we can do is you consider a half-circle translated operator and assume that you are computing a correlation function that involves this half-circle translated operator. Okay, and then you have this correlation function. You have an insertion which that is actually a translated operator, and some dot. many local insertions at some distance far away from it. Okay? Or you can even assume that there is no local insertion. And then what you do is you substitute the expression of U in terms of density matrices. Okay. And now we want to identify a path integral description by saying that this parameter minus IT that appear here are continue to get n. Basically, T you continue to minus I. Like again, like in the path in the replicator. And you look at this path integral. This path integral can be, or this correlation function can be given a path integral meaning by replacing each density matrix with its associated path integral description. Take a W plane and choose some appropriate cuts in it. Okay. So you get this kind of a description. So you have there's some modification of the replica kind of trick, okay, where you don't have the replica symmetry. So you can construct such a saddle, and you think that this half-Fourier translated operator, the correlation function that involves this half-Fourier translated operator can be thought of as a path integral done on a different surface, on a surface which I call SD. So this will be thought of as a trivial saddle for the full path integral, and the geometry is obtained this way by doing an appropriate glue in the right locations. So now, so we can specify what is this Riemann surface. So the point is that your correlation function calculation now is a CFT correlation function calculation on a different geometry. Okay. So now I assume that this path integral that I have here is a saddle point approximation of some other path integral, the full path integral in JT gravity. Okay. And this path integral may have to satisfy certain criteria just to make sure that the full definition of RHS, the half-Fourier translation full path integral, they must form a continuous symmetry group. Okay. So based on that, we have to constrain this path integral. You cannot write down an arbitrary path integral and claim that this is going to describe half-Fourier translation. So those criteria I haven't listed down because I haven't studied whether the half-Fourier translation exists within the full JT gravity or not. But I'm going to assume that when I take a saddle point approximation, there I can explicitly tell what are the criteria it has to satisfy. Because for fixed background, we know what is the half-Fourier translation. Okay. So we have to then look at the saddle of this kind of a path integral. What kind of path integrals that can give you a reduced half-Fourier translation? Okay. So the point is to construct another saddle having least free energy. It's a matter of identifying one saddle which has constant free energy. So now this phenomena that you're studying should not be really theory specific, right? The island paradigm itself is not very specific to the matter theory. So the free energy computation that we are supposed to do should not depend on the full details of the theory, right? It should depend on some universal terms.
Like central charges.
Like central charges and the contributions coming from some conical singularities, right? Like the twist operators are some contributions coming from the conical singularity. So the point is that take the saddle and look at the free energy by computing the leading or the coefficient contributions that comes from some conical singularities. This can be done. Those are universal terms. So let's for a CFT defined on a Riemann surface having some characteristic length L, Cardi already computed what should be the contribution coming from each conical singularities. Okay, so there is a specific expression for it. And the characteristic length can be understood as, let's say, if you have two conical singularities in your geometry, the distance between two conical singularities can be thought of as a characteristic length. Okay, so this is the way one can get the universal terms. Just get the contributions coming from conical singularity. So basic idea is to construct a saddle, identify where are the conical singularities, and then apply this trick to identify the free energy. So we can do that for the trivial saddle, and one can show that at late time there is a linear growth of free energy, like in the case of entropy computation. So we should look for a wormhole saddle for the geometry. So this can be done, and I'm not going to go through the details. So what one has to do is, if a geometry belongs to a JT path integral, you have to make sure that it satisfies the JT constraint. That means it should be a hyperbolic Riemann circle. And the fact that this is a gravity path integral forces you to make sure that there should not be any singularities in the geometry. It should be a smooth geometry because it's a Euclidean path integral, right? The geometry should be continuous. So the point is to see whether you can construct such a wormhole saddle. Do you have a method of constructing wormhole saddle? So what we can do is we use the ideas in hyperbolic geometry, which says that if you have a geometry, a hyperbolic Riemann surface whose boundaries are geodesics, you can get another hyperbolic Riemann surface by gluing two such small hyperbolic Riemann surfaces having geodesic boundaries and glue them along the boundaries. That will give you the hyperbolic surface. But if you are starting, for instance, if you start with quadrilaterals, hyperbolic quadrilateral, having 4 sides. So this is a hyperbolic geometry, but the point is that the tip of the geometry, the corners have conical singularities. So you can take two such hyperbolic quadrilaterals, glue them. What you will get is a geometry like a crown, which is basically a hyperbolic disk with two conical singularities. Basically a cut.
Same as PSS was saddles, right?
And so if you want, and then you can take 3 such crowns, glue them along their boundaries. That will give you a pair of lines. So this is a smooth geometry. So this is one way of constructing smooth hyperbolic Riemann circle. So we'll just do that. And so this is the kind of surface that appears when you do the replica computation. Okay.
I mean, equivalently, you have this thing with 3 geodesics and you need the edges. Okay, now, in the standard construction, you glue the asymptotic regions to the 3 boundary. The fundamental thing is something with 3 geodesic boundaries.
Yeah.
Okay, anyway.
Yeah, so that's a pair of pan construction.
Yes.
But the point is that pair of pan construction will never give you a geometry having conical singularity.
So you need that somehow.
Yeah, but what I do is I start from.
Conical singularity.
Sorry?
Final geometry doesn't have conical singularity.
Yeah, it should not have conical singularity.
Constructed it directly, right?
But
Not by cutting and pasting.
yeah, I do this for a specific reason. Right? So let's say.
You want to count the angles.
Angles, exactly. So the point is that if I take an arbitrary 3 such crowns and glue them, I may get a pair of pans with 2 conical singularities. So I have to choose the angles correctly. Angles is alpha angles correctly. So the alpha angles must be pi by 3. Only then I get a smooth pair of pans. Okay, that is one thing. Which actually this is one way of constructing it.
This
And-
is PSS saddles, right? The standard ones.
PSSY means.
The one that you flashed in the beginning of the.
So means replica saddles, right?
Yeah.
Right. This is one example of the replica saddles. Now one can ask, okay, this can be continued and you can get more complicated geometry. That we will do. So what we do is we consider the start from the trivial saddle, which is basically a W plane here and then a bunch of another planes. So since it's gravity, the gravitational region will start connecting. Right? That is a standard way. Now I connect the gravitational regions in such a way that the saddle also has a after a translation kind of description. That means the action should be such that it should be thought of as an action using a group element, which will come later. Okay, so that there's a condition. I cannot just arbitrarily choose a saddle. I have to choose a saddle such that the full path integral should be interpretable as a half-sided translation operator action. So
Sorry, I mean, if you fix the topology.
Yes.
That you have basically surface with these many boundaries and so on.
yeah, that's true.
Wouldn't that automatically give you the Z symmetric saddle to be the dominant one?
But the point is, first of all, that's no excellent symmetry. The each copies are not copies of the same density matrices. They are copies of various different density matrices because it's actually coming from the half-sided translation operator, which is not constructed out of one single density matrix. It's
They are
constructed.
the same, right? Are they the same? What is the difference between various copies?
Various copies, their cuts are different. Their cuts are different. One is a cut for one diamond M, and another one will have a cut for diamond N. And
So
then
they alternate.
Yeah,
MN,
yeah,
like
yeah,
that.
and MN, and they're commutant also. They will also appear.
Okay.
So you should be able to construct an appropriate saddle which will satisfy all the criteria and then compute the free energy of this one.
Mhm.
So what I will do is I just take some number of crowns and some number of tree. What is it? This is actually a W plane with a cut having certain deficit angle at the end of the cut, which I call as 2 alpha. And for trees, I will have 4 cuts instead of 2. And at the endpoints of the cuts, they will have an excess angle 2. So this is assumption. So these are details. I don't think I should go through it very. Now the point is that how can I compute the free energy of such geometries? Since they don't have the simple Wissarian symmetry, it's very hard to use the twist operator calculation. One can come up with a twist operator associated with the symmetry that it has. But those kind of twist operators are not known to me. I mean, I have seen some discussions in one of the Rockmeyer's paper, but it's mentioned as if you have to, it will be interesting to compute those correlations. But I don't know, those constructions are not known to me.
So it will be Z M by 4 symmetry?
Is that, no, actually it will have the product of incidence. Because I have copies, n copies of same density matrix, then other n copies of another density matrix. So within that I have
one after the other.
one after the other. So I have to do it in a proper way. So the symmetry is not incident. It's actually a product symmetry, which I don't know what is the corresponding twist of that. But still I have to somehow compute the free energy. So what I will do is I will utilize the fact that this is a geometry constructed out of crowns and these trees, which will come with its own angles. So I just split the path integral by inserting complete set of state and look at the universal contribution coming from each piece. And it's a universal contribution, so it won't even depend on the boundary condition. So this is something which I can calculate. So for instance, if I want to calculate the free energy of the usual known saddles using this method, what I should do is I cut them into 3 pieces, the 3 crowns attached to bar.
Sorry, but what about the cross ratios? I mean, in such a geometry, you will have, it's not like a rigid geometry, right?
Yeah.
It has deformations.
Deformations in the sense, some overall possible.
Deformed complex structure will be deformed. You know, you can deform the complex structure still preserving the hyperboles. Right?
Once you have a hyperbolic geometry, then what maximum you can do is you can do marking class transformation. You cannot do more than that.
Why not? I mean,
Right?
no, in 2 dimensions you can deform it.
In 2 dimensions, each hyperbolic Riemann surface is a representation, right, of Riemann surface up to some.
Yeah, so you can
Discrete
change
transformation.
No, but no, you can change the conformal class, right? Conformal class can be changed. The conformal cross ratios can be changed. No.
No, actually the point is that I choose.
Essentially not that. Okay.
Sorry.
The the conformal shape can be
It's
changed.
like moduliers.
Yeah, shape can be changed.
No, the point is that, and that's true. I have
Yes.
lots of possibilities. I take one particular shape that corresponds to choosing a particular length for the
Yeah,
crown and an angle.
right.
That will be my parameter. So this is a class of geometries.
Okay.
So for each element in that class of geometry, compute the free energy, then identify which is the right surface by minimizing the free energy.
Oh, I see. Okay.
So that's-
you will minimize over.
I have to minimize it. So
But just to say, the ab initio problem is you have some boundary conditions corresponding to your rows or whatever.
Yeah.
Then you find semi-classical saddles.
Yeah.
Right, that would be.
right.
But here you don't quite do that because that's too complicated.
Now the point is, I don't know, I have to identify the saddle. Even replicate computation, what Hartmann and Mandelson have done is, they constructed a hyperbolic surface which has moduli parameters in it. Because like you said, you cannot fix what is a precise geometry. That's gravity, right? All possible geometries you have to identify and minimize the free energy. They have done that, and then that is corresponding to minimization will give you the identify the moduli parameter. Which moduli parameters will have corresponding.
So all I wanted to ask was that, is it that the corresponding problem is too difficult for you? That is, you allow the moduli to be variables and.
No.
minimize?
No, the point is
That's what you
no, I haven't gone to a semi-classical approximation yet.
Yeah.
I just take one class of geometries and the path integral associated to that geometry.
Yeah, I see what you're saying, but why not just go to the semi-classical?
No, for-
It's too hard to do.
I have to go to that. For that, I need to identify the saddle geometry. And identify the saddle geometry is done by computing the free energy of each such geometries and see which has a minimum free energy. That's what
I had sort of the same question as Abhijit, that is, you should just write it in terms of some set of geometries which are to some extent fixed by the boundary conditions and have moduli.
there will be infinite number of such geometries.
And then you have to extremize over that.
Extremizing the free energy.
Action, yes,
Free energy is action, right?
yes.
Log of
Is
Z.
that what you're doing?
That's what I mean. That's what I want to do.
He's doing
I
that.
said
want to
I'm
do that.
confused by your working with the crowns and all
No,
that.
some of the parameters is gonna be keep free, and then he will fix those parameters.
Yeah, exactly. I keep the
Those
parameters.
for him are the
Crowns and fills are a way of.
You didn't specialize to some region of moduli space.
No, I haven't.
No, it
No.
does feel like that.
Yeah.
I haven't done. I have
That's
to
what I
do.
was worried
No, but is it clear that you are exploring the entire modulus space?
That was my.
No,
With
that's-
these,
that's
these,
See, that's what-
I am not going to choose, look at the entire moduli space. So what I do is I choose a class of, or maybe a region in the moduli space.
That's what I feel.
And within that region, assume that there might be a saddle.
Okay, so that's what I thought, and is it because it's too hard?
It's too hard.
It's too
I
hard.
mean, it's too hard to do.
Fine, fine.
Because if I knew how to do this twist operated computation for any such geometry, then things would have been easy for me.
Okay.
And in fact, Malazine and all, they are also like specifying to certain geometries. Because it's too hard problem.
And they also don't do it honest to goodness.
I mean, they also choose a topology and then see which one within that. It's more like we know this is the answer which we are supposed to get. So look at only those kind of geometries which will give you.
I haven't studied those. Go ahead.
Yeah, related to this question, if you're considering like computing reality for classical geometry, maybe that's also a degeneracy factor. Maybe that's also what you're asking.
There's
You're
no,
trying to minimize things, right?
there is no degeneracy. They will be parameterized by moduli parameters.
Yes, but like for a given, you're saying like, it's not constant for some.
No.
No, but
You mean two geometries having same free energy? Is that what you're asking?
yes.
So I mean, those kind of things, this class of geometry, that won't happen. Anyway, this is a technical thing. Let's say you do that and do whatever you want. And I'm just saying that the method I'm trying to say, by splitting the geometry into small pieces and computing the conic contribution coming from each conical angles, are applicable even for simple geometries, and one can show that this way of doing actually reproduces the twist operator calculation. Okay, you do it for this complicated geometry, you get the free energy, and then do the minimization and see what is the result that I'm going to get. I get a particular saddle. And then
Minimizing over alpha.
minimizing over alpha and the locations of the cut. So you can do that, and doing that by specifying, looking into only a part of the moduli space, like you said.
Slice.
Yeah, right, slice. And then what we do is that wormhole saddle has a nice treated geometry description. It's like the real saddle. Only change is that for the density matrices associated to the commutant, M prime and N prime, there will be additional cuts in the gravitational region. So that's the way the saddle actually behaves. So what does that mean? What it means is that the relative commutants will start getting extended. And the extension says that it actually matches with the replica computation. So in replica computation, what happens is that certain regions are getting extended, right? So here, similar extension happened, but for the commutant algebra. For the operator algebra, M and N, there's no change. But for the commutant, there will be change. That means now the path algebra got extended. Right? Because the relative commutant is getting extended. That simply means path algebra is extended. So that is what Island predicts, Island formula. So
How do you see this extension again?
So the geometry that I constructed, having free energy, minimum free energy, has a property that the sheet associated with the density matrix for commutant has a cut in the gravitational region.
Yeah.
So now, which relative commutant, they will have slightly different lengths. So that's what I learned from the minimizer, free energy minimizer. And then we have this nice picture. Now one can ask, what is the?
So, but all this cut picture is based on some Zn symmetry, right? After taking the quotient, but all this.
No. What I can do is, you have a geometry, this kind of a geometry, right? Once you have hyperbolic Riemann surface, then what you can do is you want to study CFT only. you are no longer going to do JT path eleven. Now for computing CFT things, you can do conformal transformation and then have a slight different sheeted structure.
But it will not make it Zn symmetric.
Is it not? It is not going. In this
Yeah.
picture is not Zn symmetrical.
No, but when you talk about cuts, how did that previous picture?
No,
with
Zn
this,
symmetry is not an important thing for getting a geometry out of sheet construction, right? Sheet, the geometry is not only for Zn
Okay.
symmetric thing, right?
Okay.
So here I don't have a Zn symmetry. I get a sheeted interpretation, and that interpretation gives you an extension of relative commutant, basically extension of path algebra. And now one can ask, okay, given that, what is its effect? Okay. So what one can do is now, instead of single diamonds, even for the commutant you have two diamonds. Now you can define the operator algebra for two diamonds. Let's say for the same chiral theory. So you take two diamonds, delta 1 and delta 2, define the chiral operators. That is O plus and O minus in within delta 1 and delta 2, two diamonds. Now that algebra itself won't satisfy the Hag duality. So what you need is you need additional operators, which are so-called link operators. This is discussed in one of Kasni's paper. So for this operator algebra, you can compute the effect of modular flow. Okay, that he has done. Like in one paper, he computed the modular operator for such cases where you have two intervals. And the non-trivial property of such modular Hamilton is that it's no longer local. So you have a non-local piece which you can explicitly compute for this theory, this chiral theory. Okay, so what it is going to do is that when you do a modular flow for an operator, let's say it's in the left part, this will smear the operator to the other part, basically to the interior. And that will be sort of affecting the behavior of reduced half-circle translation after pasting. Now, when you do the reduced half-circle translation for an operator that is in the left part, not in the right part, they will be extended to the black hole interior. Okay. So that means you can write down.
Some nice, like the half-sided.
This is the operator. You can write down each pieces.
It's not local.
It's not local. It's smeared out operator. You know all the object that is appearing. This functions n and out. They can be explicitly calculated. They're too complicated, but it can be calculated, and you can explicitly compute it if you want.
And depending on whether you're picking n or n, the items of this is moving slightly.
I mean m or n means.
Like there's an m and then there's some.
Yeah. Choosing.
The island region, it depends on what.
Oh yeah, what choice of algebra you have. If you choose a different n or different n, then the island changes. So anyway, so that's the confusion. Like, so you can take an operator from the path, and then after time, if you make all these assumptions, you see that the operators will be smeared into the black hole region. Without actually, the point is that without moving through the black hole, the gravitation, you actually directly do a Mobius transformation and keep it in the path. Sorry.
Is the point that you define this new half-sided translation on the boundary side?
Yeah.
It was not the standard one because you chose this.
Yeah. Yeah.
Does that correspond to some notion of a natural type 3 half-sided translation in the boundary?
That I don't know. I haven't studied all this property.
I mean, otherwise, why couldn't I just say that let me do modular flow?
You can just do the modular flow and then realize this picture, right?
Yeah.
But the only thing is that then what about the first assertion of ideal formula? Ideal formula says that before time, I should be able to reconstruct the interior. That I require half-circle translation. I can't do that using modular flow. Because modular flows won't take you outside the algebra, right? It actually keep you within the algebra. So, if you have half-circle translation, you can actually take them inside. Or in other words, it's more like checking Leutheusser and Liu proposal, whether it's consistent with this island prediction. There could be some loophole.
Page time, your argument is essentially that modular flow will start
Ah,
involving operators
right.
inside the island.
Because it's a modular flow is the elementary thing, that
Right.
if that has some structure,
Yeah, that's what I
that's
was it really important for you to consider the half-sided case?
only for the fact, for the first assertion that before page time, I can't, I should be able to translate. That translation I can't do using modular.
It's true that modular flow before page time does not steer you to the island, right?
No, because there, if I choose any algebra, I should be able to do that. After translation actually tells you. Okay, so anyway, so that with modular flow I can't do that. So anyway, the conclusion is that we just assume the existence of algebra operators and modular flow just in quantum JT gravity, and then demonstrate the assertions of island formula. Then we should ask whether these assumptions are right or not. Can we have a description of algebra operators in quantum gravity and then associated modular flow and HSV? This is something which has to be understood. Based on this assumption, we kind of see that island paradigm can be explained if these things are true. Does that mean that there actually exists such concepts in quantum gravity? That I don't know. So all the conclusions are based on certain assumptions. Yeah, that's it.
Bottom line, did you find after the baseline say that you were able to have your commutant enlarged exactly into the island region?
Yeah, because I compute what is that region. That's what pre-energy minimization does for me.
I see, and you do get it to agree with exactly the region inside the island.
Yeah, precisely.
Because it's a different
And
kind of
only
saddle, right?
Yeah, I mean that
it's a-
saddle has to be chosen such that it has a group structure, and that saddle will precisely match with the island. If I don't use the fact that this half-saddle translation for the new saddle also doesn't have a group theory structure, then everything is good.
So but let me say that, okay, you're finding saddles in some restricted set of moduli.
Yeah.
But within that restricted set, did we find the true?
Huh.
Universe
Yeah,
theory?
that we can.
And that gave exactly this island.
Exactly inside.
What do you mean when you say group theory structure?
I mean, there is this alpha parameter, like conical axis angle. That conical axis angle has to be chosen in such a way that if I do this reduced half-saddle translation 2 times, that should be another reduced half-saddle translation. That will put a constraint on the alphas that you can. Basically, a condition like this is, and something like this will come. From this, you have to solve what is alpha. Okay, thank you.
Any more questions? Not, let's thank Roji again.